Hello and welcome back to another episode of Effective JaRu, the series where we read effective Java and see if we can translate the items presented here into idiomatic Rust. So it's item 34, emulate extensible enums with interfaces. So as enums are nothing more than a class that allows you to easily provide subclasses which also serve as singleton constants. It's obviously possible to let them implement interfaces. I think that's what this item is about. So here there is an operation interface that, as usual, just has a single function that says apply. It's kind of common to have these single method types in Java, I think, just because Java is what it is. Anyway, so we implement this, and yeah, I think the example shows you that there's an enum that is a basic operation that also implements operation, which means that for each variant you will have to implement apply, and then you can basically just implement the simple mathematical operation accordingly. And yeah, the symbol here, that's just the data that it carries, and toString is overridden to provide that symbol accordingly instead of the long name, which would be plus or a minus. So the extended operation, actually, where's the basic operation going here? Where's basic operation? I thought this extends basic operation somehow. Yeah, so apparently it also just implements operation. And now I do wonder how this is done. So this test, I don't know what it would print out. I don't know how to run this actually. Let's try. Let's build the class and let's run it. You probably want to, array index out of bounds. Oh, does it have a main? It does. Oh, and it wants to have two inputs here in order to be run correctly. Oh my, how does that work again? Running Java code. I think that was a bit Java C, no Java. Then you provide the class path here, and then the, oh my. So class path, then the class name here, which in my case is item 34 dot extended operation, and then we can provide two numbers, right? And it tells you what it can do with that. And here with the basic operation, okay, there's nothing here. Yeah, but what does actually happen? So you have T, which extends enum and operations. We have a more complex type bound here, because we also say it must be an enumeration that implements operation, apparently. And then on that generic type class, okay, so we expect a class of that type here, which probably is just the enum class. And how does that even work? I don't. Okay. In main this is called. I see. So that's not actually a unit test, even though it appeared to be one. Okay. So how does it work? We provide an extended operation for test 1, so it gives the class so that these values can be iterated on, and test 2 uses a collection. Uses a collection of operations here that kind of does the same thing. I think the idea is that you can then kind of mix the basic operation and the operation stuff. Yeah, I was thinking that he actually extends the operation so that you basically have a fancy extended operation that can do a lot more, but that doesn't seem to be the case. Interesting. I seem so surprised because I think I implemented it very differently. So we have the operation here, and I really just we have this in the basic library here. We just have this one trait that is an applicator. So this trait we actually need in order to show, or in order to allow some runtime or compile time dynamic or runtime or compile time method dispatch going on, right? This is what you usually want in these cases. Of course, in Java, everything is dispatched at runtime. In Rust, you have the option to choose which one you find more appreciated or more more suitable to your task. So anyway, in the operation, we just define all the enum variants here. As you can see from our containing module, we pull the trait applicator, which is defined here, right? So you can access this using the super identifier here, which points to the parent module. And we just import all of our own operation variants so that we can use them without prefixing operation all the time. So we implement apply for ourselves, match on us, and then just implement the respective mathematical operation in a match case. Again, matches are exhaustive, so if there's a new operation coming in, the code wouldn't compile unless we add the new operation here as well. So there's no problem with that at all. It's always safe to do matches on. I mean, always, in most cases, I guess it's safe. If you have a default case here, then obviously you wouldn't know if there is a new variant, but that's something you probably have to live with then. It's a choice you make, at least. So as ref, str is just a conversion into a statically allocated string, so that's not a heap allocated one. So toString obviously heap allocates, well, it returns a reference to something that is heap allocated somewhere. We return a reference to a string slice that is in the binary somewhere, right? So it's all compiled in. There's no heap allocation going on at all. So from string allows us to basically do the inverse operation. I think is not even implemented here. From string or parse, I don't know how that is done. No, it's not. I don't know why that, probably just for the fun of it, to show how this works. So that's just a from string trait. As an error type, we just use a string here. So we format a string that kind of says what went wrong. It's really just for the user, basically, or for the one who debugs this, to see something. Usually you would implement an error type that actually implements the error trait as well. So the extended operation is a bit more interesting because it actually encapsulates the basic operation as well. So we have one variant that is the basic operation we are talking about. We have imported this from our sibling module up here and aggregated, into our one basic variant here. And then we implement apply. The cool thing is that we can, just unpack whatever operation is there in our basic one and then call apply there, right? And we just implement the rest, exponent and reminder. And then as ref is the same thing, right? Just delegate the call where needed and implement it where needed. Same goes for the from str extended operation. So we have a little test case here. Yeah, and I mean maybe this is something we could have a look at. So because we, as a domain of a string, we have everything basically that a string could be. We have to use a default case here. So this could be problematic if we now forget to, or if we now add a new variant here, then in these cases we will be warned by the compiler that we have to put that new variant there into the match statement. But here we would just try to let our basic operation try to do that, which would obviously fail. So ideally you have test cases in place that make sure that this doesn't happen. But you know how it is. Maybe it would be a good thing to be able to iterate on your variants here, so that you can have test cases that dynamically test all the stuff without you having to add them manually. So anyway, the cool thing about this is that we basically try to use operation from string. We delegate this. And if that, this try basically returns if there's an error, and as the operation has the same error type, which is string, it's compatible, and it will just be basically wrapped into our own result type here. And in case it works, the working result, which will be the basic operation in this case, will be returned that is a valid value for being used in the variant, in the basic variant of our extended operation. So that's what the code does. It does full type checking, it does full error checking, and as usual, try is your best friend there. It's very awesome that this is there. Otherwise, you would have to write a lot more. So here's, I decided to use one test here instead of printing stuff out. Let's just, look at the code that does it. Let's go there, item 34, cargo test unit. It should be, so that passed, obviously. Let's see what it does. So we have a local function here that is using dynamic dispatch of an applicator, just to show that now the enumeration variants here, they actually implement the applicator trait. So we can use that. Obviously, you could also use static dispatch here, but I think dynamic dispatch is acceptable for this kind of test. Anyway, this is how you do it. Just get a borrow of the trait of your choice, and you will have nice dynamic dispatch going on. So what I do here just to show off is we parse from a string into an extended operation, unwrap the result because we know it will be working. If not, it would fail on us, obviously. And then we pass the two numbers here and expect 4. Same here. Here we do the same with an operation. And then we also try to use the enum variants themselves. As these are units, I mean, in this case, these are unit variants. That's all you need to get one. Whereas here, you have to basically create an actual basic instance that has a unit value of the plus inside. Yeah, and that is the test. It shows that it's working. That's how you would do this extendable enum in Rust. It's just standard because it's a full type, right? There's nothing special about it. I think it's very similar to Java because in Java it seems to be, like a full type as well. It's just a shorthand in a way to get lots of subclasses going and make sure there are singleton constants of them around at runtime. Yeah, that is that about this item. Thanks for watching and have a great day.